I will send you all the 3 lectures across today. All right. And we will also at some point of time try and discuss some of the problems that I had given to you in scalar inner products. Okay, so we will do those, and maybe a few more which I will probably give you today. All right, so we will try and do look into that sometime soon. Okay, so we have other people coming in. All right, let me just go ahead and share my screen. Yeah, Skype. All right. So now, if you remember, just 1 second, I need to admit a few more people. Okay. Yeah. Just, this is a bit strange. I think it's just one person registering as several. Okay, so we'll give it a break for the time being. So now, if you remember, what we had talked about was that, okay, I have A, okay, which is an observable, right? What that essentially means that it has a set of eigenfunctions, right? Which are, let us say we call them a set of eigenfunctions ui. They form an orthonormal and they form a complete set, right? And then what did we say? That we could pick up any wave function which represents the dynamical. It represents a dynamical state of the system. And what we could do is then write down this psi as a summation of Ci ui. And then what did I say? I said if we strictly order the ui's, strictly order the ui's, then we could just write this psi down as a, it would be equivalent rather to a column vector where we would have C1, C2, Cn. Okay, and we say that this is just 1 second, let me just admit a few more people who have come in. Okay, we basically say that this is one of the kets which represent the system. So we could write it actually. So I'm just going to put this is strictly not allowed, but we can put it like this. Okay, so this is what we call as a ket vector. All right. So now I'm going to, as I said, introduce you to what Dirac, okay, called the Bra-Ket notation. All right. So let us now go to another concept that we know, all right, which is the concept of, just 1 second, I'll have to admit two more people. All right. So we will go to another concept that we know, which is the concept of an inner product, right? Or scalar product. And what is this? We essentially have learned this as, let us say, you define the inner product between two wave functions. And what do you say this is? Just 1 second, somebody else needs to be admitted. Let me see how many, okay. So we basically write it down as a phi star psi d tau. It's an integral. And please remember, this is a number. Okay, this is a number, right? And what does it represent, that number? As I told you, it gives you information overlap area, okay, between these two wave functions. Now, if I wanted to do this kind of a scalar product in terms of this, you know, column matrix, how would I go about it? So the question that you need to ask is that how would an inner product, okay, be represented in these matrix formats? Okay, so this is the question that we are asking. How do we represent it in this matrix format? Now, the key thing what you have to remember is that it is a number. This inner product is a number. So let us look at this psi. Okay, this we are writing as some C1, C2, like that till Cn, right? We then have, let us say, this phi, which we also are writing as some d1, d2, all the way to dn. So now the question is, what would be the inner product? Let us say phi psi. Okay, what would be, how would we write it in this matrix mechanics? So what do you need to multiply to a single column matrix to make it a number? All right, so let me just stop the share over here and ask you, all of you have done matrices, right? So what do you think should multiply a column matrix which has n elements and it will make it a number? Can anybody tell me?
A row matrix.
Absolutely. Okay, so perfect. So that's really the nice answer, that it will have to be a row matrix. Okay, so let us now go back and look at the situation. So obviously we are going to now need a row matrix. Okay, so let me get back to this iScribe. All right, so I'm going to change the page. All right, and we will basically need for this column matrix, okay, C1, C2, which is representing what? It is representing, earlier we just called it psi. Now we'll say this is this, right? We will need to multiply it with a row matrix in order to make it a number. All right. Now, please remember, what is the idea? We are trying to find out this guy, right? Phi psi, correct? And what it would have been in the integral form, it would have been phi star psi d tau, correct? And what did we say? That phi we wrote as d1, d2, d3, dn, correct? And we, of course, our psi was nothing but your C1, C2, C3, all the way till Cn. So now the point is that we have to do this, multiply it with this, right? So how does that form? So we will write a row here and we will have these elements d1, but that's not good enough, right? Because please look here, there is a star, correct? There is a star. So it will be d1 star, d2 star, all the way till dn star. Okay, just 1 second, let me just admit this person. So everybody got this? This is your inner product, which earlier you wrote as phi psi, right? Phi psi, right? Now in the Dirac bracket notation, you will write it like this. Okay, this is how you're going to write it. All right, so this represents your inner product in the Dirac notation. Now let's go a bit further. So this you identify as the ket vector. all right, which is directly linked to your column matrix, correct? So now the question is, what is this? Okay, and this Dirac called as the bra vector. Okay, so please remember, this is the ket phi. From this you can go to the bra vector phi. And what does the bra vector phi looks like? It's a transpose. What do you mean by transpose? When you take a matrix and change its columns into rows, this guy has only one column. That one column becomes one row. Okay, so it will become one row, and it's not only a transpose, it is a transposed conjugate. That means each element will turn into the conjugate of what was there in the column. Okay, so this is now a bra vector. Is this clear to everybody? So for every ket vector, there is a bra vector, and vice versa. For every bra vector, there is a ket vector. All right, these are row, the bra vector are row vectors, these are column, and their elements are complex conjugates of each other. So what you essentially say is that the relation between them is that of a transposed conjugate. Okay, and these two together are set to define what is called as a dual space. Right, it is set to define what is called as a dual space. Any doubts in this? Okay, has everybody understood how we get to this idea of this inner product in the bracket notation, and how you end up defining a bra vector for every ket vector? Is this clear? I know it's the afternoon, but please don't fall asleep. Has everybody understood?
Yes, ma'am.
Yes, ma'am.
Okay, so now once we have understood this idea of a dual space, okay, um, what we will just do is we will see certain relations between them. All right, so for instance, the way you talk about transposed conjugate, you essentially, the one way of putting it is to say adjoint. Okay, so adjoint operation is essentially you transpose it, which means that you change the column into a row. And conjugation is, of course, you conjugate each and every element you replace by its complex conjugate. The two operations together, you will call it as an adjoint operation. Okay, so in other words, we can say that your, if you have a ket, okay, and you have a bra vector, the relation between them is an adjoint relation. This guy here will be a column, correct? D1, D2, so on and so forth, Dn. And this guy here will be a row with the complex conjugate elements. Okay, so this is what you say is a transposed conjugate. Right, now further, okay, so let me just go to a new page. I'll also change pages here. Okay. Further, if you were writing your, let's say, the phi. Okay. So remember, all this is being talked in terms of an observable A, which has a set of orthonormal eigenfunctions that are complete. I hope you remember what completeness is. So this guy, of course, you would have written as summation over I, say di, then ui. Okay, so these are your eigenkets. These are the eigenkets of A. Okay, so I'm not calling them eigenfunctions. I'm representing them in the ket notation. I will call them eigenkets. Okay, so these are the eigenkets of A. Now, how will I write U1, for instance, the eigenket of A? It will be nothing but, let's look at it. It's going to be 1, 0, 0, all the way to 0. Okay. How will U2 be? The eigenket? It will look like 0, 1, 0, 0. Okay. What will be UN? UN will be 0, 0, 0, dot, 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 1. Okay. So that is how you will represent these eigenfunctions of A in the ket notation, in this matrix notation. All right. So now we can write the phi as equal to di into these ket ui's, right? So how will you write this guy now? The way you will write it is summation over I di star, and then you will have to multiply it with each of the bra vectors, okay, of these. So there'll be eigenbras in some sense, okay, right? So you have the eigenkets, you take the equivalent bra vectors, multiply it with the complex conjugate of this di, and you will get the equivalent bra vector for phi. All right, so this is how it works. Let's take it, so thereby we can write that if your phi is equal to summation over I di ui, then your corresponding bra vector becomes this. Okay, this is another very important thing to remember. Okay, so let me just admit this person. All right, now what else do we need to remember? How do you actually write down any of the CIs? Okay, we will be using this notation, so we will just try and see how to do it. So suppose now I want to figure out what is one of these. Okay, I will not call it CI. Sorry, I've been using DI. So how do I write this? Okay, so what is DI? DI is nothing but one of the coefficients, okay, or the weight factors of some eigenket, correct? Yeah. So question is, how do I write this? All right. So okay, I will not use di. Let us take a specific one. We'll call it dj. Okay, because I'm using the summation factor I over here, so I don't want to use I again. All right. So how do I write dj is the question that I'm asking. All right. So the way to write it would be to take the inner product between dj and phi. What will this be? This will be nothing but inner product of dj, okay, with, sorry, I'm not getting it right. Excuse me. This is what comes of being a bit addled. I'm going to take a drink of water. I'm writing all rubbish. Okay, so let's get back to ground again. I want to figure out what is dj. So the basic way to do it is that I will take the bra vector uj and then multiply it with phi. Okay, so I'll take the inner product with phi. What will this be? This will be nothing but uj, and then I will have to do it for this summation, right? This summation of di ui. Okay, so maybe I can write it like this. All right, doesn't make much sense, so I will write it like this. Okay, so how does this work out? This will essentially be summation over I di uj ui. Now we know that these are eigenfunctions of a Hermitian operator, right? So A is an observable, and as I told you before, moment I say observable, you should remember that it is Hermitian. So thereby, these eigenfunctions form an orthonormal set. If they form an orthonormal set, then what will happen? Over here, I will get di delta ji. What is delta ji? I've told you before. This is the Kronecker delta function. When j is equal to I, it is 1. When j is not equal to I, it is 0, right? So thereby, this is going to be, this Kronecker delta function is going to be 1 only when I is equal to j. Remember, I is the one which is changing, correct? The I keeps changing. J is a constant. So thereby, this will only yield you dj. So in other words, you have now an expression for dj. It is nothing but uj phi. Remember, this is just a number. Okay, inner products only give you number. So what will be dj star? Okay, we know, I'm going to write over here. Okay, I'm going to write over here. We know that psi phi is equal to inner product rules. Please remember, phi psi star. Okay, this was one of the rules. Similarly, please remember psi phi, okay, will be equivalent to, okay, or rather this star, we can write it as phi psi. Okay, so it is a similar kind of expression in the Dirac bracket notation. You change the order, you're essentially doing a complex conjugate. All right, so this di star will be nothing but phi uj. Okay, so this is basically two things that you should remember, very, very important. Okay, because we will be very often replacing these coefficients here, this one and this one, with this expression and with this expression. Okay, so before I move on, I'd like to know whether you have understood all of this. Okay, have you understood? If you haven't, we will try and go over this ground again. Have you understood? Yes, no, very good. Let me stop the share and ask everybody. Yeah, so have people understood? Have you followed this? I've tried to go a bit slow, but I think it's a little important, and if need be, I'll go even slower. Not a problem. Okay. Any doubts, please? Has everybody understood what this is all about?
Excuse me, ma'am.
Yeah, please tell me.
Di into delta ij, you have written as dj, ma'am.
Supriya, can you speak up a little bit? I think my volume is also down. Just hang on a sec. I will increase my volume. Okay. I think I'm not hearing too well. Yeah, no wonder. We're sitting at 50% volume. All right. Um, okay, Supriya, please repeat your question. I'm very sorry. I couldn't hear you the first time. Please.
Okay, ma'am.
Yeah.
Ma'am, like di into u delta ij, you have taken as dj, ma'am.
Yes.
Can you repeat that how to take the dj, ma'am?
Okay. I will tell you that. All right. So let me just go to the iScribe once again. All right. So just hang on. I will share my screen again. Okay. See, I think this is a recurring doubts that people are having. All right. So let me just change the page and I will tell you why, how that is happening. Okay. See, when I put a notation like this, okay, you all know this is a summation, correct? You with me right now, Supriya? You can see, right? This is a summation. So what do I mean by a
Yes.
summation? If I write I and I write DIUI, what does this actually mean? It means that I have D1 U1 plus D2 U2, right? Plus D3 U3. Like that, I will go on till the last number. Okay. If it is infinite, I don't have a last number. If it is Dn, then it will be Dn Un. Okay. Like right now, then let us take there are only n of these eigenfunctions. All right. So this is what you have. Okay. This is what I mean by summation. Now what I am doing is that I am trying to find out what is dj. All right. So please remember, this is nothing but this phi. All right. This phi I'm writing like this. Now I want to find out how to write down this dj. Now this j, let us take it to be, you choose a number. Okay. Don't take a very large number. What do you want j to be? Tell me.
7, ma'am.
7. Okay. So let's say j is equal to 7. Okay. All right. So now we want to find out what is D7. So what I'm saying is that to find out D7, okay, you do U7 phi. Okay. What will that be? That will be nothing but U7. And then what is this phi actually? It is nothing but summation over I, di, these ui's, correct? Yeah. So this is going to be nothing but U7, all right? And then I will put in this expression here. Okay, so which will be what? D1 U1 plus D2 U2 plus, so dot, there'll be one D7 U7, correct? Plus dot, DN UN, right? Everybody with me? You're
Yes.
getting me, right, Supriya?
Yes. Yes, ma'am.
Okay. Now let us open it up. So we will get D1 U7 U1 plus D2 U7 U2 plus dot. Over here we'll get D7 U7 U7 plus dot. Then you will get DN U7 UN. Okay. So far good.
Yes.
Now
Yes,
let
ma'am.
us see. What will this be? So it will be D1. The first one will be delta 7 1. Correct? This will
Yes,
be
ma'am.
D2 delta 7 2 plus some dot in between. We'll get D7 delta 7 7. Correct? Plus you will get Dn delta 7n. Now what will this one be?
Yes, ma'am.
7 is not equal to 1. So it will be a 0. Correct? So this will be 0.
Okay.
Plus again 7 is not equal to 2. This will also be a 0. Plus here 7 is equal to 7. That will be a 1. So we'll get a D7 dot. Then this will be again 7 is not equal to n. So we'll get again a 0. So the only thing that survives is a D7. Okay. So the
Yes,
D7
yes.
is nothing but U7 inner product with phi. Written like this in the Dirac bracket notation. Is this clear now?
Yes, ma'am. Thank you.
Okay. Any more doubts, please ask, okay? Because better to get it clarified. Otherwise, I'll start writing all sorts of stuff. And then, if it's not making sense to you, I'm not doing this for myself. I'm doing it for you. Okay. So it's very, very important. Like Supriya, please come forward and ask me doubts. It doesn't matter. Okay. I'll take time. I'll explain it to you. Have other people
Yes,
understood why it is working out like that? Yes,
yes,
no,
ma'am.
everybody's gone off to sleep. Okay, I'll assume that you have understood. All right. Okay. Please, if you have doubts, stop me, ask me. Okay. I really appreciate it when you ask me doubts. Okay. Because then at least I know you're trying to follow. and it really helps. Otherwise, what am I seeing over here? I'm seeing a whole bunch of black boxes, and I can only hear the sound of my own voice. I'm not sure what is happening. Okay. It is very disconcerting. So in class, at least I can see your expression. You look confused, you look happy, your eyes, become big. I know that there are things. Yeah, Priyanka, you have a doubt. I thought I saw a raised hand. Priyanka?
It's by mistake, ma'am.
It was by mistake. Okay. Yeah. So, I mean, you had doubts? Yes, Chandan Kumar. Please ask.
Ma'am, why should we transpose only phi, ma'am, not psi?
See, the point is, I mean, um, what are you transposing? Okay. So, again, let me just explain to you. I'll just go to the iScribe once again. So it is not like you are trying to transpose only one and not the other. Okay. What you're trying to do is to get an inner product. All right. So the question is, what are you trying to do? Okay. So let me just go to a new page. All right. Are you trying to find out, for instance, phi psi? Okay. In this case, if this is written as a column vector, say C1, C2, like that till Cn. And if this phi, okay, this phi is written as D1, D2, all the way till Dn, then you will write this inner product phi psi as D1 star, D2 star, all the way till Dn star into this matrix, right? C1, C2, Cn. Now think about what this will be. It is this row multiplying this column, right? So how will we get it? We will get D1 star. You all know matrix multiplication, right? Plus D2 star C2 plus like that Dn star Cn. Okay, so this is what, and this will be one number, right? Now here you have transposed phi because you wanted this scalar product, right? But suppose I wanted psi phi, then what would it be? I would then have C1 star, C2 star, Cn star, and then I would have this, right? Which would be nothing but C1 star D1 plus C2 star D2 plus Cn star Dn, correct? Yeah. And you
Yes,
can
ma'am.
see this is going to be nothing but phi psi conjugate. Okay, so it depends upon what kind of a scalar product, inner product you are trying to find out. Okay, depending upon that, you will make a transpose conjugate of one of those vectors. It depends on what you want. Okay, so it's not that you always do it for phi and not for psi. Nothing like that. Okay, it depends on what inner product you want. Is that clear?
Okay,
Did
ma'am.
I
Thank
answer
you.
your question? Okay.
Yeah, ma'am.
Good. Anybody else? Any other doubts, please? Any other doubts? Okay, so let's move on further. And I'm going to now tell you how to write the completeness that we were talking about. Okay, we have been talking about completeness, and we will try and see how to write down this completeness in the Dirac bracket notation. Okay, so that is the, and it's in a very nice, neat form. Okay, otherwise it's such a boring thing, right? You have to keep saying, oh, you pick up any like wave function which represents a dynamical state of the system, and if you are able to write for any wave function that it is equal to summation of ci ui, then we can say that this ui is an orthonormal, is a complete set. Sorry. Okay, you can say that. So instead of saying all these boring things, it would be nice if you could just have a very precise, concise statement of saying it. And that is called the closure relation. Okay. So I will now explain to you how to write down the closure relation. So let us just get to the iScribe once again. All right. So let's write down what the closure relation is. So let me just spell it out for you first. So we are going to now do what we call as the closure relation. And this is basically a way of talking about the completeness of a set of eigenfunctions. Now, of course, I'm not saying it specifically, but over here, I haven't said it in the statement, but you know what eigenfunctions we are talking about. It's not just some random set of eigenfunctions. These are the set of eigenfunctions of an observable. Once again, remind you, what does that mean? That means that these set of eigenfunctions form an orthonormal set, and they also form a complete set. Again, so let me just write it down. It means that they are an orthonormal set, and it means that they are a complete set, right? So if I write these eigenfunctions as some ui, then I know that when I say orthonormal set, I'm going to now write it in the Dirac bracket notation. Ui, uj, inner product is equal to delta ij. We know that. And the other thing is that pick up any psi belonging to the vector space. I have told you how we talk about the vector space. Then psi is equal to summation over I ci ui. If I can do it for each and every psi belonging to phi, then I say that these ui's are complete. Okay. Yeah. So this is basically what we are talking about. So now the question is, how do we express this in a easy manner? All right. So the way we do it, okay, I'm going to take this statement itself. Okay. I'm going to take this statement itself on the next page, and I'm going to work with it. Okay. I'll just go to the. So please remember, how are we know that for every psi belonging to the vector space, I can write psi equal to summation over I, say some ci ui. Okay, I can do this. I know this. So now let's progress from here. What did I tell you ci was? Ci was nothing but, it was nothing but ui with psi, right? All of you remember this? We just talked about it, okay? So ci is nothing but ui inner product with psi. So now let us put this expression of ci in this expression, okay? I'm going to put it there. So what will I write now? I will write psi on the LHS is equal to summation over I. Now instead of ci, I'm going to put ui psi ui. Okay, so what I have done is that I have replaced ci with this expression. Okay, so I hope everybody has followed me. Somebody. Okay, now what I'm going to do is I'm just going to reorder. Okay, I'm not doing anything interesting or anything, you know, very complicated. I'm just changing the order in which I'm writing it. I can write it as summation over I ui ui psi I. Okay, so what have I done? I have essentially written this second, and I have written this guy first. Okay, that's all I have done. Now, if it is a complete set, okay, if these ui's is a complete set, this expression psi equal to summation over I ui, ui, okay, is true for every psi belonging to the vector space, right? We know that this is true. So in other words, please look at it. You have psi here. Then you have this entity, okay, which is like acting upon this psi, right? So, and this is true for every psi belonging to the vector space. So what does it mean? It is as if this thing here is acting like the identity. Okay, so this is your identity. So all of us know an identity operator. It is an operator when it operates on something, it leaves it unchanged. So essentially, this here, okay, this thing here is leaving the ket unchanged. All right, so it must be equivalent to the identity operator. So this, what I have written over here, is what is called as the closure relation. And it is a compact way of saying that the set of UIs is complete. Okay, it is a compact mathematical way of saying it. So you can say the closure relation proves or is a compact way of writing down that a set of eigenfunctions is complete, or it is a way of showing the completeness of a set of eigenfunctions. Is this clear? Has everybody understood the closure relation? It looks complicated, but it is just a very easy way of saying that a set of eigenfunctions is complete. Okay? So remember, when we now have A, which is an observable, we know that its eigenvalues, let me repeat again, are real. We also know that the eigenfunctions form an orthonormal and as well as a complete set. So how will I write it? So if set of UIs are eigenfunctions of A, then all I need to write down is that UI uj is equal to delta ij. What is this proof of? Orthonormality, right? And I can write that summation over I ui is your identity operator, and that is proof of completeness. Okay, this is essentially this relation we call as the closure relation. Okay, I'm sorry it looks so ugly at the end. Oh my god, yeah. All right, so is this clear? Yeah, Akshay, you have a question, please.
Ma'am, the set UI, it's not a set of eigenfunctions, no, ma'am. It's a set of eigenkets of A.
Yeah, correct. So eigenkets, that's what I told you earlier, right? That the eigenkets, you can basically, how you can write, how you can take eigenfunctions and write them as eigenkets. Correct? You
Okay.
remember I wrote those column vectors?
Yes, ma'am.
Yeah. So it's still not a, I mean, okay, so go on, tell me now.
No, ma'am, I just had that doubt. If you can
Yeah.
represent
So
an
what you can do,
eigenfunction.
see, the point is, I mean, it's a, okay, so you remember I told you, I'm going to write over here itself in this page. So going to be a bit messy. This is going to be 1, 0, 0, right? Correct. So let's
Yes.
imagine it's 5. So similarly, your U2 is going to be nothing but 0, 1, then let's say 0, 0. Let's imagine it's only a 5. So just try this, okay? Just try this particular relation. Okay, imagining that U1 is like this, U2 is like this. Take their transpose conjugates, find out what each of these elements will be, and add them up. And you will see, you will get the 5 cross 5 identity matrix. Okay.
Okay, ma'am.
So that's what it is. But
Okay.
you should be able to do it for each and every vector which belongs to the vector space, or every wave function that belongs to the vector space, every ket that belongs to the vector space. Okay, only then you will be able to make the statement, this closure relation. Okay, otherwise it won't work. Is this clear?
Yes, ma'am.
Okay, any other doubts, please? I'm really happy that you people are asking doubts. It makes me feel very good, because I know that you are listening and you're trying to understand. So please ask doubts. Okay, don't be scared. I hope I'm not scary. All right. I sometimes shout, but I'm not. Hopefully, I'm not scary. Actually, I very rarely shout. That's what everybody says. Okay. And I want to keep it that way. So if I have any doubts, please ask. Okay. It makes me, as I said, feel really good that you're listening to me. Everybody is okay with this, the closure relation? Okay, fine. So let us now just go on to a little more about operators. All right, and we will try and so here we are going to come to a very key question. Okay, I have a wave function. I operate and operate let's say an operator A on it. Okay, and then I operate B on it. Or if I operate the B first and then the A, will I end up getting the same result? And this is a very key thing that we have to now talk about. All right. So just let me, I think I'm missing the time. All right. Oh, we don't seem to have much time. All right, doesn't matter. All right, so let's go a little bit more on operators. All right. So I'm going to write down, we'll have to do a little more on operators. Now, firstly, we learned that the matrix representation of a wave function is a column vector, right? It's a column matrix, correct? Now, the question I can ask you is that, okay, what is the matrix representation of an operator? All right, and I don't know whether you have guessed it already. So I have something, let's take an eigenequation. Okay, so that's the first thing to pick up. So what is an eigenequation? It says that A operating, right now I'll put it as psi, is equal to some number times psi. So what is the form of A, I can ask, okay? What can you have which operates on a column vector and ends up giving another column vector? Please remember, it cannot be as simple as multiplying it with the number. All right. So what can you multiply with a column matrix and give another column matrix? So can somebody tell me? Think about it. All of you have done matrices. So somebody did tell me that yes, you take a row matrix, multiply it with a column matrix, you end up getting a number. Now I'm saying that no, I don't want a number. I want to multiply something with this column matrix and get a column matrix. So can somebody tell me what that entity will be?
Identity matrix.
Not an identity matrix. An identity matrix will give you exactly the same column matrix, right? You're right. It is identity
Constant.
matrix will give you. It's a kind of an operator. In fact, we are going to talk about that operator. So that's a good answer. But in general, can you tell me what it should be?
Constant.
Constantly, that's what I'm saying. Constant, if you multiply, there is not much. See, what did we say an operator is? An operator can operate on this column matrix, right? constant is not going to do that, right? It's just going to multiply each and every element by that constant. And then you remember what we said about multiplying everything by a constant in a wave function. It doesn't change the meaning, right? So yes, constant is an option, but it's not the right option. Anybody else?
Square matrix.
Yes, absolutely right. It's a square matrix. Okay. So when I multiply a square matrix into a column matrix, I will end up getting another column matrix. So operators in matrix mechanics has the form of a square matrix. Okay. So let me just show it to you on the iScribe, and maybe, sorry, I don't know what I tapped. I'm tapping all the wrong things. Okay. Okay. So for instance, everybody can see my screen. So if I have now a square matrix, okay, like this, and I'm multiplying a column like this, okay. So let us say I have some A11, A12 like that, okay, till A1n. Then I have an A21, A22 till A2n, and this way it goes on. And here I have AN1, AN2, all the way till ANN, right? And this I'll have my C1, C2, like that till Cn. So what will this give me now? I will take the first row and multiply it into this column. So I will get A11 C1 plus A12, sorry, A12 C2 plus like that. Okay, I don't have space over here, so I'm not writing it. But you will realize that this is just one number, right? Then you will have A21 C1 plus A22 C2 plus you will add on till you go to A2n into Cn, correct? This is again another number. So you end up producing another column matrix. So operators in matrix mechanics, okay, just like the wave functions got translated into column vectors, the operators are becoming square matrices. Okay, so I hope that idea is correct. It's sitting with you. Since some of you came up with it, I'm hoping that it is settled with you. Okay, that the operators are going to be your square matrices. So now let us think about, so forgetting about all this, let's not worry about it all now. Keep it in your minds. Let us just learn about certain kinds of operators and certain kinds of operations on operators. Okay, we can also do operations on operators. So the first operator we can talk about, of course, is an identity operator. One of you already talked about it, and it is a very important operator. We already saw it in the closure relation. And what is this identity operator? Normally we'll represent it as an I. And it is that if you do an I on like this, we will end up getting just the same wave function. So it is only one of the kinds of operators. So it is definitely an operator, and it's an identity matrix which represents this identity operator, but it is only one kind of an operator. Okay. Then we can talk about product of two operators. Okay. So let's talk about, so I said we will talk about operators. We will also talk about operations on operators. So this product of two operators is a very important thing. Okay. So suppose now I have an operator A and I also have an operator B, and I am going to now make it act upon, let us say, this particular entity. Okay. What does this actually mean? It means that I have this phi. I first operate B on it. Why? Because B is closest to phi. All right. So then this will form some kind of a wave function. Everybody agrees with me. The operator acting upon this ket will give you another ket, just like I showed over here, right? What did I show? That the square matrix acting on this column matrix will give you another column matrix. So this will give you a column matrix, or it will give you a new wave function. On this now you operate A. Correct? So what is then B A phi? this is going to be, you take phi, you operate A on it, and then on that you operate B. So the question now is AB equal to BA? And the answer is not necessary. I don't know whether I spelt it correct, but it's not necessary. Okay. So in general, AB is not equal to BA. If AB is equal to BA, then we say something special. We say A and B commute. Okay, we will say that A and B commute, right? And we also define something about with this A and B. We define something called as a commutator. Okay, so please take a look at this word carefully. It's a commutator, and this commutator is written like this: square brackets A comma B. Please remember the comma, just like in the inner product, is very, very important. You don't put the comma or you don't put square brackets, you put round brackets, the meaning completely changes. You know, round brackets, two entities with a comma between them means inner product. You put them with those triangular brackets with that line in between, it still means inner product. But if you do this square brackets A comma B, this is defined only for operators. Those were defined only for wave functions. This is a commutator. And what is this? This is nothing but AB minus BA. Okay, this is definition. It's a definition. Okay, it's a definition. So you define the commutator of two operators A and B as, what is it? AB minus BA. So obviously, when A comma B is equal to 0, then A and B commute, right? This we know. Okay, then A and B commute. All right. So please remember this thing of the commutator. And now we will learn a few properties of the commutator. Let me see what's the time. Okay, so I think I've run out of time. We will just do the first property. So properties of commutators. And the first property is that commutator AB is equal to minus commutator BA. How do we do that? That's because AB is nothing but AB minus BA. Commutator BA is nothing but BA minus AB. Okay, which is equal to minus AB minus BA, correct? Which is equal to minus A commutator B. Okay, so that is the proof. So we will learn about a few more properties of commutators, and we will also learn the significance of commutation. Okay, so there is a lot of physical significance of commutation, and this is with respect to measurements. Okay, so we have to ask ourselves that if I made one measurement on a system, so why do you do operations? Because you want information, right? What is this information making? It's a measurement. So you have to ask yourself that if I make one measurement first and then another measurement, so I want to measure, let us imagine, position. So I measure position first and then I measure momentum. Or I measure momentum first and then I measure position. Will I get the same answer? Will my measurement still be the same? So this is the question that you're asking. And this is why you need these commutators, not because somebody likes doing all this mathematical jiggery pokery and, confuse everybody. It's not that. You really need to know these answers. Does the wave function remain, the information, does the first operation actually do something to that information, so that when you do the second operation, you will not get the same as if you had done the second operation first. Okay, it's a very, very important question, and this is what we will try and address in the next class. Okay, so I will stop the share, and if there are any further doubts, please ask. We will clarify, and then we will end this. Are there any further doubts, please? Any doubts? Okay, I think everybody's kind of saturated with quantum mechanics today. So what we will do now is, so we will stop this class. Everybody can put in your attendance. And I will wish you all a very, very happy Yugadi tomorrow. Enjoy your festival, please. And but remember, stay safe. Okay, that's very, very important. It's unfortunately very tough circumstances that we are going through. And I think we will come out through this much stronger, much finer. So wishing everybody a wonderful festival. So have a great time tomorrow. But as I said, overall, remember, keep to the norms and, stay safe. Okay, all of you. So take care. So I will just close off now. Once you finish putting in the attendance, I will end the meeting. Okay, you can start leaving.